Okay, so my story is a little different. It's a scientific adventure story, if you like, about a voyage into the unknown. It's about particle physics and our quest to understand the universe better than we do already. And what that means is for the next 20 minutes or so, I'm going to give you a really rapid zip through our subject in terms of what we know already, but importantly, what we're trying to find out. And this is such an exciting time in science at the moment, because really, for the first time in about 20 or 30 years, we now have new experiments, most notably the Large Hadron Collider that I'll spend a lot of time updating you about, that are for the first time giving us new data that will give us new insight into some of the mysteries of the universe that I'll be telling you about. So I'll be giving you the latest news from my subject, and then you can judge for yourselves about how well we're doing. Now, to put this in context, particle physics is a study of the universe. We want to know how it ticks. And the approach we take is to study it from the very smallest subatomic levels. So we think that everything in the universe, and this includes you and your iPads and everything else, is made of the same basic stuff. Not just atoms, but the same basic ingredients of atoms, fundamental particles. And it's our aim to identify what these are and to understand their behavior. And from that very low level, extrapolate out and understand the behavior of the universe as a whole. Now, we already know quite a lot about the universe, which is sort of summarized by this picture behind me. So we think that about 14 billion years ago, it started in a Big Bang. And the very early universe at this time was tiny, very, very hot, very, very dense, and formed not of stars and planets, but of their ingredients, the ingredients of atoms, the fundamental particles I just mentioned. And then as time went on, everything expanded, cooled, matter coalesced into more familiar forms until here we are today. Now, we know most of this from scientific observation. The rest is conjecture. And most of this observation comes from telescopes and probes through the realm of astrophysics. But if we really want to know what makes matter tick at the very smallest scales, how the universe behaved in the very earliest times, then we can't do that with telescopes. We have to recreate those very hot conditions in the laboratory. And we do this with particle accelerators, and that's where particle physics comes in. That's the angle and the take that we give. So we already know quite a lot about the universe. We know that everything we see in it is made of the same 12 basic types of particles, 6 quarks and 6 leptons. Can you hear me? I have the impression my microphone is going. There, is that better? Good, okay. 12 fundamental particles. These form all matter, all stuff in the universe, and these are held together by a small number of fundamental forces. There's the weak force, responsible for radioactive decay, and everything feels this. There's the electromagnetic force. That's most familiar to us in everyday life. It's driving the projector. It sort of drives society as well, acts on anything charged. And there's a strong force, which only these particles called quarks feel. And it's a strong force that holds atomic nuclei together because it's an attractive force, and it's strong enough to overcome any electrostatic repulsion that the protons in the nucleus feel. And that's basically it for particle physics. But it's not all there is to the universe, because, I've forgotten gravity, which is quite important. But from our point of view, at the very tiny distance scales we probe, gravity is so much weaker than the other forces that we just tend to neglect it. So we even have a picture for how these forces stick matter together. We think a force is conveyed by means of an exchange of a force-carrying particle that's exchanged between matter particles, and we have a theory that encapsulates this mathematically into a set of equations which we use to predict what sort of fundamental particles might be produced in our experiments and how they behave. And this theory is really, really good. It's so good that we haven't yet made an experimental measurement that disagrees with any of its predictions. It's so good that we call it the standard model of particle physics, which is building us up for a bit of a fall, because good though this theory is, we know it's not the whole story. It's incomplete because it doesn't contain gravity. We don't even know if it's right. We don't even know if our understanding of the universe is correct. There are many unexplained features. Let me give you some examples. The first problem that hits us concerns understanding the very easy but fundamental properties that everything has. Take mass, for example. You've all got mass, it's what gravity acts on. And our fundamental particles have mass, because we know that, we measure it in experiments. But our theory, our wonderful theory, predicts that nothing should ever have mass, which is clearly not the case. So we don't understand this. But we do have a theory that tries to explain it, not a new theory. It was put forward in the 1960s by many people, amongst whom was a man called Peter Higgs. And this theory tried to explain mass as something a fundamental particle gets by means of its interaction with a new particle, a Higgs particle. And the amount of mass you get just depends on how strong that interaction is. It's quite a simple idea. And in fact, this theory is part of our standard model of particle physics, and we actually need it to make our predictions make sense. But it is just a theory, because even though it's played its part in every single successful prediction that's been verified by experiment, we haven't yet verified its one experimental prediction, which is the existence of this Higgs particle. We've never seen it. We've been looking for it for years and years and years, and it hasn't appeared. And that is a real worry, because if we can't find the Higgs, then we can't be sure that it exists at all. And if the Higgs doesn't exist, then the theory that predicts it must exist, well, that has to be wrong. And if that theory is wrong, then so is our standard model that is built upon that theory as a framework. And at that point, we know that nothing makes sense anymore, and we really have to go back to the drawing board. So that's why, whenever you hear about particle physics, you almost invariably hear about this search for the Higgs. It's because it's the missing piece in the jigsaw of our understanding of matter, the final link that we're missing. Without it, we don't know if we're on the right track or not. It's not the only problem, though. We also don't understand that much about the stuff we can see in the universe. Take antimatter, for example. We think that half the universe was made of this strange stuff in the Big Bang, but yet we hardly see any of it around now. And that's weird. Now, what we do know about antimatter is that when it meets normal matter, it just annihilates. So if I have 1/4 gram of antimatter meeting 1/4 gram of normal matter, then the resultant explosion has the equivalence of 5 kilotons of TNT. Amazing. We don't see it anywhere, though. But that sort of annihilation process went on all the time just after the Big Bang, releasing photons of energy that would then split to give more matter and antimatter that would then annihilate. And this repeated until the universe was about a minute old. And by this time, it had cooled down so much that there was no longer enough energy to prolongate this battle between matter and antimatter. And everything stopped at that point. And what remains in the universe now is just a consequence of a very tiny difference between the amount of matter and antimatter that existed at that point. Very, very small. No more than 1 part in a billion. But it's the reason why we're here. Because if there was no difference, the universe would just be full of light. So we need to understand what made antimatter that tiny, tiny bit different to understand the evolution of the universe. And more than that, we know that everything we've looked at is a tiny fraction of the universe. Much more of it is made of dark energy, dark matter, which we have no idea about. But at least we have theories that predict what dark matter might be made of, and these give us predictions that we can try and test in our experiments. And so on. We have so many open questions about the universe. In fact, the more you look at it, the less we actually know at all. So how do we move on? How do we make progress? Well, we do experiments. I'm an experimental physicist, and so I work at a facility that gives me access to an experiment that could provide answers. I work at CERN, the European Centre for Particle Physics, which is just up the road. And although this started life as a European centre, it's now a global centre, because particle physicists from all 5 continents work together here. And it's very exciting at the moment because it's home to our newest experimental facility, the Large Hadron Collider. Now, you've probably heard about this because it's become slightly newsworthy. It's a monstrous machine. I think it's the largest piece of continuously connected scientific equipment in the world. It's one of these phrases that comes with so many caveats that they probably aren't wrong. It occupies a 27-kilometre-long tunnel, circular tunnel, 100 metres under the ground, that is only a few kilometres from where you're sitting. If you look at this map or this aerial photograph behind me, you see the Alps in the background, you can see Lake Geneva, and Geneva's just nestling somewhere in the middle, top third of that picture. You can see how close you are to the path of the LHC. Now, if you're lucky enough to visit, or if you're going on the visit tomorrow, you might actually be able to go down into the LHC accelerator. And if you do, you'll find yourself standing in a tunnel like this. You'll see a long chain of blue magnets. These are the heart of the accelerating facility. And you'll just see that slight curvature in the distance, because this tunnel is so big, you just cannot appreciate the scale until you get down there. Now, what goes on in this machine when it operates is that we have two beams of protons, so that's the nuclei of hydrogen atoms, accelerated in opposite directions around the ring. And they're accelerated to enormous energies, so that by the time we reach design spec, these protons will be going at 20 kilometers an hour, less than the speed of light, really fast. And then when we've done that, we bring them into collision at 4 points around this ring, where we build our experiments. And the idea is that in every single one of these proton collisions, that happen not just once or twice, by the way, but about 40 million times a second, in each one of those, we recreate, for a very small instance of time, in a very tiny area of space, the very hot temperatures last seen at very early times in the universe. And if we can do that, that means that we can replicate matter in terms of the fundamental particles it existed in at that time. Our experiments take snapshots of what was produced, and we analyze millions, billions of these snapshots to infer what matter was doing at that time, to get a better understanding. Now, what's notable about the LHC, why it is so special, is that it's the most powerful particle accelerator we've ever built. And that means it's capable of recreating the conditions just billionths of a second after the Big Bang. It allows us to look back to such early times. We've never been able to do this before. That's why it's so exciting. So, that's all wonderful, but big question, is it working? You may remember that we started up briefly and abortively back in 2008, and then we had to shut down rather quietly for about a year to fix it. Well, last year we started up again really in March at record-breaking energies, and yes, much to our relief, the accelerator has been working really well. Now, we're not performing at design spec yet. We're only running at half design energy, and when we started off, our beams had very low intensity. We're gradually ramping up performance so that we can be sure we understand it. So by the end of the year, we were up to maybe 20% of the nominal intensity values. And this graph you can see here shows that the rate at which the experiments collected data increased exponentially as a function of time. It's a log plot, that's why it looks like a straight line. Now, last November, we switched running modes to collide not protons, but lead ions. And the idea there was to provide a better replication of the early universe in a denser environment. So the experiments have data, and we've been analyzing it. Now, analyzing it, of course, we have to start from scratch. It really is like going on a voyage to a strange land without a map to guide you. You have to make up your own rules to analyze it. So we started off by analyzing snapshots of particles whose properties were really well understood, who could provide us a sort of standard candles that we could use to evaluate how we were doing. And there are two pictures of them here, of a W and a Z boson, the carriers of the weak force. These have decayed to a type of lepton called a muon, which is very characteristic and easy to see. 1 muon in the case of a W, 2 for the Z. Well, so much for the obvious. But once we know we can do that, we can start making measurements, we can test the standard model. Remember, we want to find out where this theory breaks down because we know it's not correct. We need to find that crack that gives us the hint to where we can find a deeper, underlying understanding of the universe. So we've tested the forces in the standard model. The strong force, first of all, we've counted the number of times we see quarks in our experiments. And this plot shows you how often we see quarks as a function of their energy as measured in different regions of the ATLAS experiment. But the bottom line is that the data points match up beautifully with the lines, which are the standard model. It holds. It holds for all the forces, quite disgustingly. So we can turn our snapshots of W's and Z's into measurements of those forces. And these are pictures produced by the ATLAS, CMS, and LHCb experiments. They all look slightly different, but they have the same bottom line, which is the data follow the theoretical prediction. We haven't seen anything wrong yet. Now, of course, as we get more data, because we haven't collected much so far, we'll be able to probe this more precisely. But so far, it looks good. So fine, but what about our known unknowns? What about the Higgs? Well, of course, we're not being quiet about this. We're actively looking for it. But we don't have enough data to see this yet. And what we've done is, all we've done so far really is work out how much more data we do need to see it. So this picture encapsulates a study where the experiments have worked out how much data they need to be able to either rule out the whole existence of the Higgs and our theory, or to provide the first hint of its existence throughout the whole region where we expect to find it. And what we found out is that by the end of next year, we should have collected sufficient data to be able to explore most of the possibilities. So that by the end of 2011, 2012, we should be able to tell you whether the Higgs exists, doesn't exist, whether we understand the universe or not. And our competitors over the water at the Tevatron in America will be able to do the same job on the same timescale. So this is the most exciting time we've had in particle physics for ages. We haven't had a new facility for 20 or 30 years which is really capable of pushing back our knowledge. And now we really are standing on the brink of being able to say something quite fundamental about the universe and how we understand it. So this is all to come. You're going to have another talk in a year or two to see exactly what we've found. So that's the known unknowns. But importantly, we also look for the unexpected, the unknown unknowns. Because, remember, we want to find out what's out there. So we want to search for dark matter. We want to search for extra dimensions of space and time, evidence of strings, would there be any. And these are really long-term analyses. They'll take years and years and years and years to do the best search that we can. But it doesn't mean that we haven't started them already. We have. It's just we haven't seen anything yet. And I just put this plot up because I wanted to reassure any of you who might still have some sort of residual concern that the LHC is going to manufacture black holes when we get going. Well, embarrassingly, it's one of the first things we looked for. Having told the world we didn't think that there would be black holes being produced, it didn't stop us actually having a look. And this is a null result, so don't worry about it. We've confirmed that there aren't any black holes that we can think of. So, which is reassuring. So much for our search into the unknown. But what we found along the way is that we've seen other things that are completely unexpected, that we have no prior knowledge of and no expectation for. So I mentioned in November we started running with lead ions to provide a better simulation of the early universe. And that gave us something really unexpected and interesting. When we looked at those collisions and we looked at how particles were distributed as they flew outwards, we saw something we never would have imagined. We saw that these particles seemed to know about each other, that they weren't distributed randomly, that there's a very strange spatial correlation there. They're all grouped together in certain regions. It's like there's a coherence effect. Now, what we think this might be is evidence for a new phase of matter that's being produced as our free particles start to liquefy into more normal things like protons and neutrons that we're more familiar with. But we don't understand this at all. It's completely new. And we're still analyzing the data and still developing the theories to put context to our results. So hopefully, when we've collected more data again next year, we might be able to have more insight into what went on in the very early universe as our fundamental particles started coalescing on their way to form atoms. That would be really wonderful. And finally, just a note about antimatter, because I mentioned that at the beginning. We also need to understand that if we want to understand how the universe evolved. Well, the LHC will try and investigate antimatter, but we don't have enough data yet to really pin it down. We've made observations of it, but we need more statistical precision to be able to pin down any differences between the behavior of matter and antimatter. But we have had results in the past year, not from the LHC, but from another experiment at CERN called the Alpha experiment. And this published something rather astounding in November. So for the first time, Alpha has managed to trap a sample of antimatter and hold it for a reasonable amount of time. Now, it's not much, it's 40, well, not even 40, 38 anti-hydrogen atoms, which have been held for 0.2 of a second. So it might not seem like much on the scale of Dan Brown's Vatican-defying angels and demons amount of antimatter that can hang around for 24 hours or so. But this is a real technology prover, because we've never been able to isolate anti-atoms before. And by having a sample there, we can make direct measurements of how they behave, instead of looking at them once they've been somewhere and disappeared and inferring what went on, which is the approach we have to take at the LHC. So with more data here, now that we know we can study it in this way, hopefully we'll be able to get more information on antimatter and understand what went on in that vital first minute of the universe. So that's my summary of the latest news. Very exciting. We have a new facility that's yielding data which is starting to unfold and push back the horizons of our view. We are really on the brink of being able to see further into the universe. And it's such a fast-moving subject that although I wrote this talk and last updated it 1.5 weeks ago, it's already out of date. So disregard most of this. What's actually happening is that the LHC is running not just this year, but next year as well. Full tilt. And we're doing that because we think by the end of 2 years, we'll have enough data to really rule out or discover the Higgs. Very important to know whether we're on the right track at understanding the universe or not. And we might also have a good crack at seeing evidence for dark matter as well. So we don't want to stop until we've got there. And then we'll have a year's break to upgrade the accelerator. So the bottom line is you should expect some very, very interesting results to come out. However, I can't tell you what, because this is research. This is research into a regime that we've never studied before. We've never looked at matter at such tiny scales before. We've never looked at the universe at such early times. And to be quite honest, we have no idea what's in there and what we'll see. But what we do know is that the LHC has brought us along on a voyage of scientific discovery. Whatever we find out will tell us more about the universe. And I hope in this very, very brief talk I've been able to give you something of a flavor of our science and what's involved and what we're searching for and why it's so very interesting at the moment. Thank you. In the very earliest times, then we can't do that with telescopes. We have to recreate those very hot conditions in the laboratory. And we do this with particle accelerators, and that's where particle physics comes in. That's the angle and the take that we give. So we already know quite a lot about the universe. We know that everything we see in it is made of the same 12 basic types of particles, 6 quarks and 6 leptons. Can you hear me? I have the impression my microphone is going. There, is that better? Good, okay. 12 fundamental particles. These form all matter, all. Okay, so my story is a little different. It's a scientific adventure story, if you like, about a voyage into the unknown. It's about particle physics and our quest to understand the universe better than we do already. And what that means is for the next 20 minutes or so, I'm going to give you a really rapid zip through our subject in terms of what we know already, but importantly, what we're trying to find out. And this is such an exciting time in science at the moment, because really, for the first time in about 20 or 30 years, we now have new experiments, most notably the Large Hadron Collider that I'll spend a lot of time updating you about, that are for the first time giving us new data that will give us new insight into some of the mysteries of the universe that I'll be telling you about. So I'll be giving you the latest news for my subject, and then you can judge for yourselves about how well we're doing. Now, to put this in context, particle physics is a study of the universe. We want to know how it ticks. And the approach we take is to study And the very early universe at this time was tiny, very, very hot, very, very dense, and formed not of stars and planets, but of their ingredients, the ingredients of atoms, the fundamental particles I just mentioned. And then as time went on, everything expanded, cooled, matter coalesced into more familiar forms until here we are today. Now, we know most of this from scientific observation. The rest is conjecture. And most of this observation comes from telescopes and probes through the realm of astrophysics. But if we really want to know what makes matter tick at the very smallest scales, how the universe behaved, be it from the very smallest subatomic levels. So we think that everything in the universe, and this includes you and your iPads and everything else, is made of the same basic stuff. Not just atoms, but the same basic ingredients of atoms, fundamental particles. And it's our aim to identify what these are and to understand their behavior. And from that very low level, extrapolate out and understand the behavior of the universe as a whole. Now, we already know quite a lot about the universe, which is sort of summarized by this picture behind me. So we think that about 14 billion years ago, it started in a Big Bang.